Hello, this is the 15th video in my little series on Fourier series, and we're going to look at the Parseval's identity. And this is the last video in the series, probably for quite a while. I may at some point come back and do examples or applications or something like that, but for now I think this is going to be the last one in the Fourier series. So we're going to kind of treat Parseval's identity in two cases. One when we have an orthonormal basis of functions, and the other is orthogonal basis of functions. So here we're going to let the partial sum of this linear combination of our orthonormal basis functions, it's going to be the partial sum with Fourier coefficient Cn. And that is where I think video 4, we talked about orthogonality and how we derive the Fourier coefficients. So if this squared distance between these two functions is 0 in limit, then this identity holds. So the sum of the coefficients squared is equal to the integral of this f of x squared. So let's do it. So by F10, which is Bessel's inequality, we know that the squared distance, which is the inner product of those two functions, is equal to this. And then if this holds, this limit holds, so the limit of this, which is equal to this by F10 equals 0, like our assumption, then we could subtract this to the other side, and then those two equal, and we're finished. So now let's look at it in the orthogonal basis case. So here, if f is continuous and has period 2 pi and has a Fourier series, then this relationship holds. And again, this is Parseval's identity. Now, we're going to kind of show this two different ways. One is sort of silly, and that means that if we look at video 10, part E, we show the relationship between the CNs and the AN and BNs going from an orthonormal basis to an orthogonal basis, and we show the exact relationship. And actually we pretty much prove it in that video that these two equal. And so if we just say, hey, go look here, we're technically finished. But I'm going to prove it a different way, which I think is pretty unique. And we're going to look at F10 again, part C, and in Sn is the partial sum of the Fourier series. It says that the squared distance between our target function, what we want to estimate with this series where we use the Fourier coefficients, and any other function of linear combination of our basis functions, this square distance is always bigger than when we use the Fourier coefficients. Now Cn is what we defined in video 14, the Casaro sum of these partial sums. Then, since the squared this is the inner product, so this means this. So we integrate from negative pi to pi of this function, which is this, squared. It's less than or equal to, we integrate this squared. Well, if we take the limit on both sides and let n go to infinity, we get this. Now, in video 14, we showed that this Casaro sum of the partial sums actually converges uniformly to f of x. So this inner product, or this, converges to 0, which says this converges to 0. Now we're almost there. So this limit converges to 0. But in F10, we showed that this limit was equal to this. And if this limit converges to 0, then we can take this to the other, to the other side of 0, and we get this. And then we're finished, and the proof is done. Now, there's technically quite a bit more we can do with Parseval's inequality. And matter of fact, I think there's an if and only if, that if Parseval's identity is true, then the series converges and vice versa. So, we're not going to look at that. But if you want to do it on your own, you're welcome to. That's it. I've so enjoyed this series. I hope you have. And that's it. See you on the next one. Thanks. Bye.